YouTube. Okay, now at this point, just to again situate our discussion in relation to our previous class, our discussion is situated about 300 million years after the Big Bang. So that is the era where your quasars were actually formed, and you know that is highly related or correlated with the birth of your stars. Here on this screen, as you can see, is a very famous diagram in astronomy. So we call this the Hertzsprung-Russell diagram. Now, I would like you to focus your attention on the x-axis. And on the x-axis of the diagram, as you go towards your right, you get increasing temperature. For example, you start from 2,500 and then 5,000, which is the range. By the way, these are in Kelvin, 5,000 Kelvin, which is basically where the range of the temperature of our sun is. And there are 14,000 Kelvin, 20,000 Kelvin, and some 30,000 Kelvin. Now, what I would like you to notice about the position of the temperature is that it's quite unconventional in the sense that as you go from your direction from the right towards the left, you have an increasing temperature there or increasing value in your temperature. And that is quite unconventional in mathematics because we are used to plotting it in increasing order from left to right. But I would just like you to note of that distinct plotting of data. And also, if you try to focus your attention on your Hertzsprung-Russell diagram as you go up towards the y-axis, you are actually seeing an increase in the luminosity. And for ease of comparison, it is set here that 1 will be the luminosity of your sun. Okay, para paspas ang comparison nimo. Meaning, if you are trying to compare the luminosity, for example, of this star A here, or let's say the star B, you could just compare that luminosity with the sun. And later, you will get to understand kasi pasabot tag luminosity. So basically, this Hertzsprung-Russell diagram, particularly on the luminosity, is plotted in this manner for ease of comparison relative to the sun. Okay? So these are some of the important quantities that you have to understand. As I was saying earlier, you will get to understand what luminosity is. Now, as you can see on your screen, luminosity is the intrinsic property of the star. So this is actually related to the amount of light emitted over the star's surface area. So that is your luminosity. So we say how luminous is the star, for example. Now, there are some factors affecting luminosity, and the first one is how large how large is your star. So, as you can see here, by the way, class, your large stars, hopefully, you can now answer. Now, there is really a relation between your luminosity and size. As you can see for the supergiants and the giants, they are on the upper part of the Hertzsprung-Russell diagram. And do note that if you are in the positive, more like the upper portion of the y-axis, and again the y-axis is in luminosity, you get higher luminosity. And as you can see there, that is where your giant reside. Your supergiants, your giants, and larger stars reside on the area where luminosity is high or very high luminosity, because as you can see here, your luminosity is actually a function of how large your star is. And when we talk of how large, we are actually talking about the radius of your star, because your stars assume a spherical shape, or for simplicity, if we assume that the star has a spherical shape, just like what I am sketching here, syempre, the size of the star, how large your star, is a function of its radius r here. That's what I am trying to write here, radius r. So, syempre, as your radius is increasing, for the case of very large star, they tend to be very luminous, as what you can see in this Hertzsprung-Russell diagram. And also, when you try to understand again, the amount of light emitted over the star surface is also high. Daghan ang or ang quantity sa light nga i-emit sa star surface. So that is also telling you that the luminosity is somehow related to how bright your star is, or how bright your star will appear to you. So mas dagko sila, mas bright yun na sila. And I think that is very easy to follow because that's something that is logical, and it's, like it's something that we can connect with our daily experience. For example, if naa kay headlight sa mong sakyanan, syempre kung dako kayong headlight, dako gid pud kayong light nga imong makita, or siga kay siya. Kung gamay pod na kay flashlight nga gamay lang, um makita nimo nga gamay pod yung light. So that's why I am confident na dali ra na makuha that luminosity is a function of how large your star is. Secondly is how hot. Now, if you notice here in your Hertzsprung-Russell diagram, as I've said, as you go from the left in your x-axis towards the right, from the right towards the left of your x-axis, you are actually seeing an increase in height. Increase in temperature. Now, if you also look into that class, tawag gani. Diba, ang second factor is how hot, as you can see here. How hot it is. That is a factor of luminosity. Now, let's try to illustrate or try to understand the relationship between how hot or the temperature of a star and its luminosity. Now, do note that, as you can see here, ang imong mga stars class na medyo relatively colder, they tend to reside and have the color of red and orange, yellow. So by the way, natay red, no? Mo na atong pinaka-cold. Ang sunod orange, yellow, wala kay green, blue, and white pa di ay. Roy, walay green, ang white, ang mupulian na niya, dayon na kay blue. So kana sila. So this is the coldest sa imuhang mga stars. So red is the cold one, and B is for the hotter one. So mao ni sila ang mga init nimo nga mga stars. But when I say red is cold, it doesn't mean that it's something na cold in our daily experience. As you can see there, that is still, for example, for the red stars na nasa mong main sequence, it's 2,500 Kelvin. And that's very large from our daily experience, right? But anyway, as we can see here, class, as your temperature increases, makita sab nimo unsa man nga posible nga, or ang trend nimo ba, magkasaka imong temperature lang, tawag gani ini diri. I'm gonna use yellow. Magkasaka imong temperature padulong diri, unsa may nakita nimo sa luminosity niya. So nakita sab nimo nga ang imong star tend to go upward in this direction. Subot pasabot, take note na ang imong y-axis, nagpasaka sila sa ilang y-axis ba? When they are rising in the y-axis, that implies that their luminosity also increases as the temperature increases. Okay, but as you can also see in this case, class, dilibot pasabot nga, unsa na, maura na ang isa ka factor niya, because as you can see, although it's true, you can see here na magkasaka ang temperature aning imong mga star, nagkasaka po ilang luminosity sa y-axis. Kaya nagsaka man na sila diri nga direction ba sa imong y. But also, ang isa gyapon ka factor kung imong lantawon diri, although naarang ang temperature range niya diri, class, ato lang siyang ikuha ng temperature range, no? For example, sa imong giants ug supergiants na red ug orange nga stars nimo, although naalang dira ang temperature range niya from 2,500 to 5,000 Kelvin, you can still see the general pattern nga as your temperature increases, pasaka man ang temperature nimo diri, di ba, towards your left. So magkasakay mong temperature padong sa left, magka luminous gid imong object. So I am hoping you are seeing that relationship from the Hertzsprung-Russell diagram. I'm just going to erase some things there para di ka siya hugaw. So to summarize, basically we have observed that as your temperature increases, your luminosity also increases. The same with your radius or the size. And of course, the third one, this is quite easy for you to understand, that the luminosity is a function of how far it is from the Earth. Since we are the observer, and we already noted that one from our experience nga nakay truck ba, nakay car that is very far from you, and then it's emitting a light. And then of course, pag lantaw nimo ba sa layo siya, gamay kay ng light, or dili nimo, not gamay, but faint ang light nga imong makita. Pero pag magkaduol na siya, of course, our common experience is telling us that it will appear very bright. So that is why its distance from the Earth is also affecting its luminosity. Now, luminosity can be mathematically represented by this equation, and you will be using this in your problem set, where your L is just equal to your sigma, which is a Stefan Boltzmann constant that will be given in the problem if there is any problem. A is the surface area of your sphere, and that is just 4 pi r squared. And T is your temperature in Kelvin. Now, take note that everything that we talk about in the factors affecting luminosity can be simply summarized in this equation here. So it's a function of R. That means to say linearly related, directly related with R. As the radius of your star increases, the luminosity also increases, or the amount of light that is emitted on the star's surface area. And a significantly larger effect is its temperature, because take note, the power or the exponent of the temperature is to the power of 4. So dako kay gyud na siya effect ang imong temperature dai class kumpara sa imong radius or size sa imong star in terms of the effect on the luminosity of your star. Again, to summarize everything, this is your equation of the luminosity of the stars. It's just the Stefan Boltzmann multiplied by surface area T to the 4. And then when we talk of luminosity, that is the light emitted, or the quantity of light emitted over the star's surface area. Now, another quantity that you must understand or differentiate from other quantities is the absolute magnitude. When we talk of magnitude, we are simply referring to the brightness of the star. So when we talk of absolute magnitude, it's the brightness of the star if they were at a standard distance. Because do note that your stars are actually sparsely situated in vast and different distances from us. So wala gyud na sila galinya nga giingon ana from the earth. So that is why our concern here is unsaon man nato pagkabalo, how will we quantify unsa gyud kinsa gi mas bright nila nga possibly if one star, let's say star A, and this is, for example, this is Earth, and we have star A here, and then star B, and then star C. Take note that how we view these stars vary from their distances towards the Earth. So the question that baffled us is this question: how will we truly quantify which of this is the brightest sa 3? Kaya syempre kung maglayo siya sa imo, muhinay sa iyang brightness as perceived by us. So ang buhat mo na to na class is we will more like, of course, use our mathematical devices to have these stars A, B, and C aligned, for example. So if I have the Earth here, akong buhaton na unsa man kaha, I will ask this question: if I will align star A, star B, and star C at the same distance gikan sa ako as observer in the Earth, how will each of them appear to me? So how will their brightness appear to me? So that is what you call absolute magnitude. So that's why it's a measure of the star's brightness if they were at a standard distance. And the standard distance that we are talking about is 32.6 light years, which is equivalent to 10 parsec. Okay, so that is how you measure the absolute magnitude. So kumbaga, unsa gyud tinuod nga brightness niya if the same sila distance diri sa Earth. Okay, because of the fact na akong gi-highlight diri no, as your star magkalayo sa ato nag-vary man gyud na naiduol na ilayo. So dili gyud na siya, how they appear to us is not really their true brightness, di ba? So mao na nga kung gusto ka sa absolute bright magnitude or absolute brightness nila gyud, what you will do is to align all of them. Of course, dili gyud align physically, no? Kay di mo man ta makabuot nga ato na silang ipalinya then i-observe. Ang atong ginabuhatan na class is natay data, atong gi-simulate ang data, what if they were located at 32.6 light years? How will their brightness vary, or how will their magnitude vary? So that is what you call your absolute magnitude. Okay, so this is also illustrated, the concept is also illustrated in this illustration here. We on the Earth as the observer, and for example the sun, the real distance is very far. Now, if we are trying to compare, for example, another star here, I will just call this um, maybe Betelgeuse or BE na lang. Ang akong buhaton, Betelgeuse, I will situate it at 32.6 light years or 10 parsec. And observe, unsa man iyang brightness tiraa if yun na iyang distance. So again, that's the absolute magnitude. I know I've been talking a lot about this, or I've been talking for a long time about this. I'm just hoping that you get the concept. Now, okay, the same. The second is the apparent. Now, take note, we are talking absolute magnitude first. This one is apparent. Then, when we say apparent, probably it's quite easy for you because this is a word that you use all the time. So, when we say apparent magnitude, it's just the star's brightness as it appears when viewed from Earth. So, basically, this is now a very qualitative measurement. Kay unsay hitsura ng imong star, unsay brightness niya kung lantawon siya dito sa Earth. And take note, the apparent magnitude is not the true magnitude, not the true magnitude sa imong star. Okay, sa apparent magnitude, syempre kung layo kay imong star sa imo syempre they will appear very dim or very very small ang light na yang i-emit kung layo kay sa imuha. Bala pag unsa ka dako ng imong star or unsa gina siya tinud-anay ka bright class. Basta layo siya sa imuha, logic will tell you na ang observer diri sa Earth will notice nga gamay ra kay na siya sa imong view or kanang very dim na sa imong view as you watch that compared to those stars nga duol kaayo sa imo. So they will also tend to appear very very bright sa imong panglantaw. So that's why when we talk of apparent magnitude, this is how it appears to us as an observer on the Earth. So one of the things that I would like to emphasize here is in terms of the measurement of the apparent magnitude, whenever you have a negative measurement, again, this is quite unconventional because whenever you have a negative value here, this implies that it is bright in the sense that the apparent magnitude of your sun is at negative 25, and negative means there that it's very bright, and whenever you go to positive apparent magnitude, that corresponds to very dim na mga stellar objects. So your sun is at negative 25, your moon negative 15, so it's bright you cannot na makita as observed from the Earth. Your Venus also is at negative 5. This is not very new to you, kay makita man yung Venus usually sa kadlawon or depende sa gabi. Pero kana siya class ma-notice gyud mo ni siya nga planet kay grabe gyud sa ka siga than the rest of the stars in the sky. And then Sirius Vega is at 0, nasa dadira. And then your brightest quasar is at more like the interval 10 to 15. So, ang imong brightest quasar, it's already very faint sa imong mata. Di na makita sa imong mata, naked eye. You are going to use sophisticated na mga telescope just to see them. And so is your asteroid. So, kung saan maglantaw ang inyong gabi class, wag kayo makita ang asteroid nga mo pass through dira. Because of the fact that the apparent magnitude of the asteroids is at the range 20 to 25 na diri as I've said, as the quantity gets more positive ang value sa imong magnitude, mas magka-dim na imong object Okay, and here spectral class. Now your spectral class in the stars basically kuan na sila 1 2 3 4 5 6 7. You have 7 spectral classes, and they are categorized according to letters. So natay 7 ka-types imong spectral class, and each of the spectral class, by the way, corresponds to the color of the star. So the hotter spectral class nga type mao na imong O. So lantawa ilang color. So blue, blue, blue to white, white to yellow, orange to red, and red. So O ang imong pinaka-hot nga temperature at greater than 25,000 Kelvin, and followed by BA. So there is actually a mnemonic on how to more like easily familiarize yourself with the spectral class. But at this point, I'm going to return to the Hertzsprung-Russell diagram. Also, dito sa imong x-axis at the top class, na naka-indicate imong spectral class diri. So for emphasis, I am encircling the spectral class type. We have M, and that corresponds to color red stars. And of course, the color also tells you about the temperature. So those with the spectral class M tends to have a relatively the coldest na temperature sa imong stars. I don't know why it's not making a perfect circle and it's irritating me. Okay, that's better. So K, these are your spectral class G, F, A, B, and as I was saying, your spectral class O are corresponding to the stars with higher surface temperatures ranging to greater than 25,000 Kelvin. So those are your O. And of course, kung great na sila mga temperature, they also correspond to the blue ng mga colors sa imong stars. Because as I was saying earlier, your coldest, red, followed by orange, yellow, then the white stars, and then the blue. Okay? By the way, basig matingala mo nung anong ka na ang order, actually makita po ni mo na siya sa daily life good class. Normally, your material, your object, for example, you have a steel. Tapos, imuhan na siyang gibutang sa fire. Kana bitang sa imong mga blacksmith. So, mag-forge kag kuan na sword, kumbaga. So, mag-forge ka na class. The first color good, basta mo saka ng temperature sa imong material, in this case, this one, it will always start with red. Tapos, kung magkainit na siya class mo, orange, good po na siya. Painiton pag yun yung mga ayaw mo, yellow. Ay, walay green, sorry. Mo yellow, then mo puti din na kadugayan, dayon blue. So basically, the same ra gihapon gyud siya. Nga progression in your color sa pagsaka og temperature. So padulong gyud na siya sa blue gihapon. But then again, probably ang ato lang ma-observe ani kay mga gagmay ra man nga temperature murag naara gyud na sa red. Mo pula lang imuhang steel or maybe orange manotice sab nato na dira nga mga temperature. And again, that is corresponding to the temperature of the material. And so, dili ta makuyawan nga nganong ingon ana po ng behavior sa imong stars because basically, these are still emitting radiation nga mga bodies. So, naagay po siya associated na temperatures. Okay, where were we? Okay, kini siya. Now, for example, kana imong Rigel no, naana siya sa constellation Orion. Am I right? Yeah, constellation Orion, that is a spectral type B. So blue gyapon na siya nga star, kinsa pa may mga si Betelgeuse na gyapon na sa Orion class. Constellation Orion, and by the way, you can always, I think this is very easy to spot na constellation, Orion the Hunter. So your Betelgeuse is actually a red giant. So spectral class nimo nga M. Now just to provide you with a little bit, to illustrate where is Orion and the stars that we are talking. So let's try to look into Rigel. And this is a blue star. It's in the constellation Orion. So I'm just going to slew my Rigel, where's constellation Orion? Here. So basically, kanang imuhang na si Mars dira. Ang kining Orion imo class na siya sa tiilan sa imong constellation na Orion. So mao na yung hitsura actually kanang naitulo ka bakos dira, mao na manotice nimo. And si Betelgeuse na gyapon na dira So Orion no kay red, si Betelgeuse na gyapon na siya sa arm ni Orion the Hunter. So kining Betelgeuse maklaro gyud nimo kani siya class nga star dira Okay, so you can actually, I don't know, maybe take a picture of that constellation ug manotice nimo na siya na naa na siya sa iyaang unsay tawag ani arm ni Orion. Anyway, so let's go back to our discussion. I'm just trying to provide some context sa mga gipang discuss na to kay basig nang lutaw na po din yung utok ba. Anyway, as you can see here, this is quite like very difficult to memorize. So a better way to memorize this, or not really a better way, but a fun way to memorize this, is to utilize the mnemonic. So basically, these are the spectral class type. Sorry. So you have O, B, A, F, G, K, M, where from M going O, that corresponds to red stars to blue stars. So basically, logic will tell you if you understood our discussion that is also corresponding to an increase in temperature. Now that is a boring way to memorize things, so maybe we will use this mnemonic. I searched this on the internet. O, be a fine girl or guy, kiss me. Okay, so that's the order of your spectral class type, where O corresponds for the hot stars up until the spectral class type M na stars for the colder, relatively colder stars. Okay, so I will be expecting na dali ra kanyo na ma-memorize dapat ang spectral class sa imong stars. And we will have a problem set where you will be, like arranging the stars dito sa imong Hertzsprung-Russell diagram given some values about or characteristic about them. Okay, once again, the Hertzsprung-Russell diagram. Now, why this is important, class, just to spoil you ahead, because the development of your, the evolution of your star will basically just be jumping from here, from this Hertzsprung-Russell to natay mga development nga maabot siya from main sequence, mo siya giant, super giant siya, dayon mo cross na pod siya diri sa imo ang mga white dwarfs. So natay mga ingon so that's why I am encouraging that you should at least pay special attention or maybe a little bit of time sa paglantaw sa imong Hertzsprung-Russell diagram, because this will be very essential in the analysis of the evolution of your stars. I'm hoping I did not sound very boring. So first question that we have to set with our minds is unsa man ang forces that stabilizes our star? Because basically you should know that the star, they are not solid at all. They are not solid. What phase they are in matter, that's for you to search, but they are not solid. So they are actually made up of ionized gases. May mention na ako, no? Ionized gases. So unsaon man nga mahimong stable ang imong gas. So what keeps the star stable? Now, if we will go in physics, technically, we will say that the star, for it to be stable, must be in hydrostatic equilibrium. So mauna ang technical term. So basically what it meant is that the force of gravity that is trying to compress the mass, syempre, although it's a gas, it is composed of very large gas collection of gases. So it has a significantly very large mass, what class? More than the mass that you can imagine in your mind. So dagko ka na siyag mass. So whenever there is a mass, you can remember in the force of gravity equation, whenever there is a mass, there is an associated force resulting from gravity. So the force of gravity will try to squeeze all that masses together at its center. So that's the first force that is trying to compress your star. Now, the question that should be in your mind, if they are being compressed by the force of gravity by virtue of this mass, that means that it must at some point collapse and be very, very small in size. Kaya syempre, gi-contract man siya sa yung force of gravity. However, there is also, as you can see, it is in equilibrium. There must be a force that is trying to balance the effect of your force of gravity. And guess what? From your chemistry class, this is your fusion. Nuclear fusion ni mga force class is releasing energy in the form of heat and light, and other form of ionizing radiation pagawas gikan sa imuhang star. So that force that is coming from your fusion is actually balancing the effect of the force of gravity. That's why your star will assume a stable nga shape nimo, just like this one, or stable nga shape or stable nga size. Now, you will also get to see later na whenever there are problems associated with the balance of your thermonuclear force. I'm just gonna write this one. Nuclear force in your nuclear fusion. Not nuclear fusion, the force of gravity. The force of gravity. So whenever they are balanced class, they are in hydrostatic equilibrium. So basically, your star tends to be stable in size in that case. Now, whenever that is not the case, as you will learn in the upcoming discussion, whenever there are some imbalances, particularly the case when the gravity overpowers the thermonuclear force because there is something happening in the core of the stars, that will lead to the instability of your star. So that will be unstable, and when it is unstable, class, you will see that the star will jump from, for example, from one classification as a main sequence, either it will go towards the giant na stage or a supergiant. So ingon ana ang mga cases nga mahitabo sa iya pag mag-unbalance na siya. So basically, if it's stable, it is in hydrostatic equilibrium, and the force of gravity trying to compress the star is just equal or balanced by the hydro or thermonuclear force generated from the nuclear fusion that is happening in the core of your star. Okay, so I'm just gonna take my coffee for a little while, and I would just like you to have everything that I'm talking about sink in sa inyo. Okay, coffee is life. Okay, let's proceed. Okay, as you can see here, class, this is an illustration of the stellar evolution of star with varying initial masses. Now, I would like you to focus on the sizes or the mass of your stars. Or not really the stars, but the more like the ingredient of your stars. Katong nasa imo ang sa tawag ani, giant molecular clouds that eventually created your protostar. Now, higher mass is on the positive Y over there, and lower mass is going here, downwards. Unsa may manotice niyo? What have you noticed in terms of the more like the lifetime of a star? Kung massive kay siya, dali ra ba siya mamatay or dugay noon siya mamatay? So lang tawag gani ang imuhang sketch class. So let's first start with a less massive. So sige, nataw na to. Kung gamay kayong mass sa imong star, just like this one, nantawa, ang iyang ultimate nga demise ana or iyang end sa iyang life cycle niya class. Should I call it life cycle? Probably. Okay, maybe it can be called life cycle. Ang iyang end ana is brown dwarf, and take note na ang time ana niya, your time increases by the way from left to right. Diri ang direction of increasing time nimo kas dira. So nakita nimo medyo dugay-dugay siya. How about for larger mass? For example, ang kining sunlight na to nga protostar just like this. Kanusa man siya mamatay. So mabalaan na to sa atong discussion also that the ultimate demise is for it to become a white dwarf. And eventually, if the universe will get very old, a black dwarf. So white dwarf. How about kung dako na gyud siya parehani? A larger mass of a protostar eventually na dead na siya diri sa imong black hole, maka-create siya black hole. A larger pa gyud nga mass, mag-black hole gyapon siya, but somehow a more premature nga time, mas dali nga time na diri ara siya nga time, kana siya nga direction ba, or kana siya nga imong time. Ang imuhang pinaka-massive pagyud, as you can see here, they tend to be dead here. So, unsa may na-notice ninyo nga trend diri So, apparently, kung dagko og mass ang imong initial nga protostar sa imong developing star, they tend to reach its ultimate demise in a shorter span of time. And we will get to understand why that is the case. Kaya basta ginyong hunahuna, kung dagko kay siya, dugay noon kay siya, kaya daghag fuel. But that will not be the case. Okay, now, this is not really the discussion yet on the stellar development for the low mass star. I just plug in this part of the slide just to provide a little bit of context sa atong mga next discussion. So, for the low mass star development, which again we will have a separate discussion, we start with a nebula that is made from GMC. So, this is GMC stands for giant molecular clouds. So, molecular clouds. So, from the giant molecular clouds, it condenses, creating your protostar. And there's something wrong with my like illustration. Okay, protostar, and then after it becomes a protostar, moadto na din na siya sa imong main sequence class. And you will get to learn that in the main sequence, ang ginatrabaho lang nimo, or you can classify the star to be in the main sequence just like our sun when it is in the process of fusing hydrogen nuclei to helium, which is the case of our sun. And after it is in the main sequence, for some reason na atong i-discuss, musaka na siya class sa imuhang musaka ang luminosity na niya kay mudako yung area, mahimo na siyang red giant. Now after mag red giant siya, which we will also discuss, mahimo na siyang planetary nebula. So this is already a sign of aging na sa imong star. Actually, red giant, sign of aging na niya. And then planetary nebula padulungay na gid siya sa iyang ultimate demise, which is to become a white dwarf. And eventually, kung magkadugay ang white dwarf class, kay ma-lost niya na tanan nga radiation or energy nga naa niya, so eventually it will turn black. So wala na may energy nga iyang gi-give off, mahurot na ba, sumanang mo itom na siya. So kung nag-forge pa ta og kuan na ni steel ba, nag-forge pa tag steel ni class, so init kay siya, so naputi siya. So eventually ang kanang kainit nimo dira will be radiated away, so mubalik ng steel sa imong color, original color niya, whatever the original color is. So mao sa nahitabo sa imuhang white dwarf na as it radiates energy away through time, it will also give off heat and eventually become a black dwarf. Now, a funny thing, our universe is actually very young. Bata pa yung guys siya class for black dwarfs to develop. So currently, we don't have black dwarfs. Black dwarfs. Okay, bata pa kayo itong universe. So in the upcoming years, probably, not the upcoming years, but more like in the next, I don't know, billions or trillions of years, we will have finally our first black dwarf. Katong mga tigulang na gyud kay nga mga stars. Okay, so there are some important concepts in physics that you have to learn to understand the evolution of the stars. Kay para makasabot mo ngano, mutuog yun mo ba nga? Ngano din nga nang nahitabo because anything that happens there could actually be or is better explained first in physics before sa astronomy aside. So first concept that you should note is the concept of the conservation of the angular momentum. And by the way, this is a universal law. So kung tinuod ni siya sa Earth, tinuod ni siya sa Mars, tinuod ni siya sa any region sa atong universe. So the conservation of your angular momentum is best observed. I don't know if you have tried. Kung nag-roller blades mo class, mas dali man ang roller blades no or nakatry mo skating sa SM, manotice ninyo na or kung ma-observe mo ka nang nag-skate na tao bitaw. For example, nagpatuyok siya no tapos gi-open niya yung hands. Ani magud nga case when it's i-open yung hands, the masses are distributed. So kung ingon ana ang case ana niya class, you will get to learn in your upcoming physics, maybe in your senior high, that the moment of inertia is also very high in that case. Kaya naka-distribute man widely ang imong mass. So pag tuyok ka na niya, it tends to have some specific na angular velocity which you call omega. So meaning kanang pag-rate sa iyang pagtuyok lang na siya unsa ka paspas iyang pagtuyok. Now kung imong kamot gani class or naka-notice mo or naka-try mo ani or naka-observe, kung imong kamot sab imong i-close unsa may nahitabo ani, your masses are not very scattered or distributed. Kay imuha man gisulod imong kamot sa gi-close imong kamot sa imong body ba. When that is the case, when you are initially spinning at the angular velocity omega, ayaw mo kawala sa term ha, ang point lang ana niya kay gaspin ka with omega, pag ipaduol nimo ang kamot bahalag walay external force nga ga-act sa imong walay outsider ni action ni magpatuyok ba. Tuyok lang jud ka initially ug ana nga kapaspason pag move sa imong kamot sa towards the center of your mass, the effect of that is the moment of inertia will be decreased. Then ang net effect in a class, just for emphasis, is the omega, which is just the angular velocity sa imong pagtuyok, will be increased. Kay imuhang angular momentum L is conserved. By the way, your L is just I, moment of inertia, times the angular velocity. So, if conserved na siya, that means LF is equal to L initial. Angular momentum final is just equal to angular momentum initial. Sabot pasabot, let's just do some basic mathematics there, Ang I nimo is just moment of inertia 1 or initial, a final man din ang first, no? Final, angular final is equal to moment of inertia initial and then the initial angular velocity. Now, if you are going to find for the final velocity, you just have I initial, moment of inertia initial, omega initial angular velocity divided by the final moment of inertia. So may final moment of inertia nimo, syempre your final moment of inertia is decrease. Kaya ano man, imo ka man ang gipag-close imong kamot dira, so the masses are not very scattered. How about your initial moment of inertia? So syempre ga-open imong hands, the masses are scattered, and in effect, the moment of inertia is increased. Your initial velocity, wa kay mahiwana, kay constant man nagihatag no initially. So ang net effect ana sa imong WF, if you try to analyze the equation, this will consequently tell you that the omega F, ang imong pag-spin ana karon kay mukusog yun na siya. Mupaspas na ang pagtuyok nimo, class. And I would like you to take note because in the context of the protostar development from your giant molecular cloud, that is a very relevant na concept, the conservation of angular momentum. Now, take note, I'm just going to zoom out here. The giant molecular cloud of gas and dust in interstellar space, syempre, initially, your masses are very much distributed. So pareha na ni siya katong sa ice skater nimo nga nag-spread out iyang kamot, meaning na spread out pod iyang masses. So eventually, of course, the laws of physics will really dictate na kanang imong giant molecular clouds must not be static. Nagtuyok gina siya sa space, class, galihok gina siya dira sa space nimo. Pero as the force of gravity will try to squeeze that towards its common center of mass padulong dira, unsa may nahitabo? It's just like the skater initially trying to pull its widespread arms towards sa iyang breast area or sa iyang, not breast area, but sa iyang, there is sa iyang area sa iyang lawas, class. So, ang mahitabuan na niya, syempre, just like the giant molecular cloud nimo, mugamay ang iyang distribution sa masses. Kay mas na-concentrate na siya diri sa tunga. So, going back to the analogy of the rotating nimo nga ice skater, ang imuhang angular velocity or kapaspason sa pagtuyok sa imong giant molecular cloud will start to speed up. Magkakusog na siyang tuyok. Taman sa i-compress pag yun nag-ayo sa force of gravity. So, syempre, the masses will be more concentrated. The moment of inertia also will be decreased in that manner. Sa mahitabo, magkapaspas yung ka ng iyang pagtuyok niya, class. Sumutuyok na siya og paspas kayo because of the conservation of angular momentum. And eventually, maunang from the giant molecular cloud, you are able to create your protostar dito sa tunga. So this is not yet a star. That is just your protostar. Okay, just like this one. So eventually also, just like our sun is just a star. Eventually some of the protostars in its development will eventually form planetary system, just like what happened in our sun. But not all will be able to do that. So again, this is just the point that I'm trying to make in the development of your protostar. That is just the angular momentum in action. That means as your masses becomes more and more concentrated, the moment of inertia is decreased since the masses are not spread out anymore. And the consequence is you have an increase in angular momentum. So, paspas kayong pagtuyok sa imong giant molecular cloud in that case. Okay, when I talk of giant, I'm not talking about IT nga large ha, or Earth nga ka-large. Very, very large yun ng mga sizes, class. Okay, another thing. Why does the protostar eventually assume a spherical shape? Nga naman yun nga, ang mga large na to mga stars usually mag-assume man yun na siya spherical shape. Now, the very common answer is you will reason that, of course, sir, the gravity will try to squeeze them towards the common center. So, syempre, if the force of gravity is acting radially towards the center, so ang mahitabog yun na is a spherical nga shape. But aside from that reasoning, the answer comes from the geometry of the sphere. So, if you try to look into the geometry of your solid sphere, class, or a sphere, a sphere actually has the minimized moment of inertia among all of the shapes that you are seeing here. So, for example, basig mo ana mo ganahan mo a universe or star nga murag rod ang iyang shape. So, a rod shape na star will have a moment of inertia which is 1/3 ml squared. If ipatuyok nimo siya yung center, 1/2 ml squared. But among all of these geometries, ang imong solid nga sphere, maunay pinakagamay yung guys siya og moment of inertia, 2/5 mr squared. So, tungod kay gamay kay siya moment of inertia, class, mubo kay siya moment of inertia, paspas kay ni siya. You need a very small or minimal force para mapatuyok nimo na siya. Minimal force to rotate. And as I was saying probably in the class, ang ato yung kalibutan or atong physical laws are designed in such a way that it will always minimize the energy. For example, your electrons na naa sa imuhang excited state will tend to decay back to the ground kay mas stable man gyud ang ground. So, ma-learn po na nyo sa physics nga nung nag-increase ang entropy kay nga naman mao po na yung minimum nga energy nimo. So, mauna nga ingon ana gyud ang system nato perminti. So, ani nga case man gud ang solid nga sphere nimo mao na siya minimize ang iyang pinaka-minimum nga moment of inertia for a given nga volume. So, mauna nga paspas kay mapatuyok or dili paspas. Dali ra kay nimo siya mapatuyok by requiring a minimal force. So mauna nga in the development of your stars later, ma-realize nimo nganong mag-sphere man gyud siya. Kay gumubo kay na siya moment of inertia. Paspas nimo na siya patuyokon. And take note just a review from your physics class, inertia diba is the resistance to change in state. So meaning to say if ga puyo ko gusto ko magpuyo ra ko forever. If galihok na ko gusto ko magpadayon na po og lihok, that is your inertia. So whenever your inertia is small, that means the resistance to any change is small. So dali ra kay siya mapatuyok nimo. So that is why in the case of your protostar, the most sensible physically and geometric na shape para sa imong stars is to assume spherical shape because again, minimum ang imong moment of inertia. So small ang required nga force to set it rotating. Okay? Another question, why does it eventually flatten out? So I was talking for around 1 hour. I was thinking na makaya na ako nig 30 minutes. But anyway, second question that you have to answer from Kuro Sensei is, why does your protostar eventually flatten out? Just like in the development of this giant molecular cloud that you're seeing here. Have you watched some YouTube videos in baking? Ka-notice mo na class if you're like making a dough somewhere here and then maka-notice mo sa mga baker, I don't know baker ba tawag ana, kung ilahan ng ipa-rotate gani, manotice nimo class whichever the direction of your rotation, in this case padulong in this direction, kung asa ang perpendicular nga direction ata niya didto mo flatten ang imo ang mass. Mao na nga eventually kaning imong dough nga lingin kayo kung ipatuyok nimo na siya mo tend gyud na siya to flatten. And that is still explained by physics, no? So the answer to that is the masses on the outermost region of the sphere. So assuming this is your protostar, perpendicular gani, the masses on the outermost region of the sphere perpendicular to the axis of rotation. In this case, this is your axis of rotation. I will just name Y. This is your axis of rotation. Dira gatuyok ang imong entire masses. Ang direction ana niya class perpendicular, you will learn from your physics class, is experiencing the greatest tangential velocity. So kung great kang tangential velocity, that tends to flatten out the original distribution of mass or sa imong geometry ana. Kung asa ang area nga dako kayo ang imong tangential velocity, mura man na siya kung naapay mass dira, malabay siya ayo dira aba. Mauna nga kung diri ang imong axis of rotation perpendicular to the axis of rotation, which is this one, the one I am highlighting in yellow, that tends to be the region na ma-flatten out siya. Okay, so this helps us answer why nga kung imong lantawon diri sa imong protostar development. Syempre, of course, if we assume that this is the axis of rotation sa imong star, sa imong protostar, but di pa siya star, no? Protostar pa lang siya. Kaya wala pa siya niabot sa main sequence nga stage nga mag-fuse na siya og helium from 2 protons. So, as you can see here, if you assume that this is your axis of rotation, dapat naka-physics na gid mo no para mas sensible sa inyong panghuna-una ang discussion. Pag tuyok ana niya dira class, pangitaon nimo ang direction sa perpendicular sa axis of rotation, which in this case is this one. For emphasis, this one here, this one. So dira mo flatten out ang imong distribution sa mass. So mauna nga after assuming a spherical nga shape, because this is the minimum na moment of inertia nga geometry, your remaining masses will tend to be flattened out in the direction in the direction perpendicular to the axis of rotation, which in this case, this is your axis of rotation. So, mao na nga dito na siya mo-flatten out. So, just like our Earth, mao na nga atong Earth, dili gid po na siya perfect na sphere, kung dili oblate na siya nga spheroid class. But pasabot, ang imuhang bulge sa imong Earth or kanang bitong murag na oval siya nga shape din ha sa imong equatorial nga region, because the equatorial region is the area nga perpendicular sa imong axis of rotation. Kay syempre our Earth is rotating from north to south. Is that right? Our Earth is rotating eastward sa imong north o south poles. I think that's a better word construction. So that's why we notice that the ring area here, this is the perpendicular area or perpendicular na direction. Dito ma-flatten ang imong masses. And so leading that our Earth has that bulging part dira. Okay, so the next discussion again, or I think this will be on the face-to-face. This is the answer to the question that more massive main sequence stars means faster nga stellar death. So you will get to discuss this nganong ang mga massive nga star mao may una nga mo reach sa ilang ultimate demise than the lower masses. So just to provide you with a hint, the answer is actually something that we have already discussed, particularly on the hydrostatic equilibrium of the balance of the fusion forces and the pull of your gravitational force sa imong star. Okay, so I will be seeing you sa face-to-face on, I think, Friday, kung sakto kung paghuna-huna. And do not forget to answer the personal milestone quiz. It will not be recorded. It's just intended for you to check whether you did understand the discussion for this session. And also, do not forget that I think the quarter exam is 9, November 9 to 13. So medyo dali na gid siya. So medyo i-review na nato ang atong previous nga discussion, since the entire coverage will be everything we have discussed from the very first meeting. Okay, so yeah, see you sa face-to-face.